Next speaker is George Barany, when I think of George, I think of the saying, may you lead an interesting life, and that can be used both as a curse and as a blessing. George's parents, Kate and Michael, survived the Holocaust. They're from Hungary, came to this country and became prominent scientists. And they brought into the world George and his brother Francis. They're both professors now. And I think the interesting aspect of his life started in August 1971 when he was catapulted from Stuyvesant High, one of the high achiever high schools with Bronx School of Science in New York, over an undergraduate program, missing that and coming straight to Rockefeller. Well, we're not going to go over the trials and travails of George at that time. Again, not without interest. He is now a professor of chemistry at the University of Minnesota, and when he was a graduate student here, he worked on sulfur-based protecting groups. And when he first came, I remember him as one real crackerjack tennis player and chess player. I don't know if he keeps up with this now, but his most recent extracurricular activities include constructing crossword puzzles, and one of these was published in the New York Times this last year, so he's quite a guy. Anyway, I think I've covered everything. His talk is Chemistry of Carbamoyl Disulfides.
Thank you, Alex. Good afternoon. We've assembled today from all over the world to honor and reflect on the personal and scientific legacy of Bruce Merrifield, who ranks among the most creative and innovative pioneers of modern chemistry and biology. Bruce was a remarkable man of modesty, grace, and courage, who so many of us counted as a colleague, mentor, friend, role model, or icon, often in multiple capacities. This afternoon's speakers have been charged to share some aspects of their own scientific lives, with an emphasis on how these have been inspired, influenced, and impacted by our associations with Bruce and with the school of gifted and motivated protégés and collaborators that he attracted as Rockefeller Laboratories. And by the way, Alex, I did not get personal permission to call him anything other than Dr. Merrifield until I'd been in the lab for about 6 years. My choice is to highlight the chemistry of carbamoyl disulfides, an area that we made relevant to the peptide synthesis field during my graduate and postdoctoral studies with Professor Merrifield, and among those that my coworkers and I have pursued throughout my independent career at the University of Minnesota. Before that, however, I want to recall for you the very first time I met Bruce, a mere 2 weeks after my high school graduation. I was enrolled in John Gregory's intense summer biochemistry course, and 6 weeks' worth of mornings were devoted to studying Albert Lehninger's then new textbook. For the same afternoons, we undertook week-long laboratory modules, and Bruce's third ever graduate student, Michael Draper, and you've already heard from Garland Marshall and Arnie Margolin, the first two, was supervising one in which we were taught how to carry out the amino acid analysis and manual sequencing of a short peptide. On July 15th, 1971, following the wrap-up of the experimental work, Mike invited me to the fourth floor of Flexner Hall, where there just happened to be a group celebration of the leader's 50th birthday. As thrilling as it was to be introduced to Bruce on that special July day, I must attach even more significance to his willingness to allow me to pursue my independent 6-week summer biochemistry project with him. These were heady and exciting times for the laboratory, since the now classic Journal of Biological Chemistry full paper by Bernd Gute and R.B. Merrifield, describing the first solid phase synthesis of an enzyme, had been published just a few months earlier. As we've heard, the machine shown here was used over a 3-week period to conduct the necessary chemical steps for assembly of the 124 amino acid sequence of ribonuclease A on a polystyrene beaded support. After cleavage from the resin, oxidation, and careful purification carried out over several additional months, a purified protein was obtained that had activity and specificity matching the protein obtained by a 2-minute method of synthesis, which had been perfected 1 billion years earlier. And I thank my brother Francis for drawing this slide. The highly significant Gute-Merrifield work along with independent work featuring solution synthesis methodology that was accomplished by a team at Merck Research Laboratories led by Ralph Hirschman, proved unambiguously Christian Anfinsen's hypothesis that the one-dimensional or primary structure of protein contains all the necessary information for acquisition of the biologically potent three-dimensional or tertiary structure. Now, ribonuclease includes 8 cysteine residues in its linear sequence, and out of more than 100 possible ways that they could pair to form 4 disulfide bridges, a single natural alignment is favored. My own initiation to solid phase synthesis that summer of 1971 was directed at a small piece from the active site of the muscle protein myosin that I studied previously in the laboratory of my parents, Michael and Kate. Bernd Gute himself, along with Anita Bach, and you may not recognize the last name, but she later married a fellow graduate student, Mark Riemann, and now goes by Anita Riemann, and is here with us today. Bernd and Anita, with wonderful kindness and forbearance, oversaw my efforts, some of which were timed around available playing slots on the Rockefeller tennis court. I used the protocols of the JBC paper, as well as techniques described in the invaluable practical book by John Stewart and Janice Young, to make an octopeptide that I subsequently showed was capable of binding ATP. Note the key role of a cysteine residue. This discovery was reported at a Federation meeting in Atlantic City and at a Cold Spring Harbor symposium, and caught Leininger's attention in time for the second edition of his textbook. Thus, through some incredibly good beginner's luck, I had my first publication with Merrifield at the age of 17. Now, this slide summarizes the essence of my doctoral work under Bruce Merrifield's mentorship. Deeply inspired by the ribonuclease work, I set as my long-range goal to apply the solid phase method to understand protein folding and function. Bruce, along with the deans and Lyman Craig, T.P. King, Bruce Erickson, Alex Mitchell, and others, all advised me to first develop some knowledge and skills in organic chemistry, and as it turned out, much more time than I'd ever anticipated would elapse before I would finally be able to tackle proteins directly. Among other issues was the so-called protection scheme. State-of-the-art Merrifield solid phase peptide synthesis relies on 2 classes of protecting groups, both removable by the same chemical mechanism, namely acidolysis. The permanent benzyl type protecting groups, including the anchor to the resin, must survive repeated exposure to trifluoroacetic acid, TFA, at each cycle of the deprotection step, the so-called temporary deprotection step, which is shown here. So you see that the TFA gives a stable tert-butyl carbocation, then the carbamide intermediate spontaneously loses carbon dioxide to give the protonated amine, and we can proceed. As a consequence, the final cleavage requires the use of liquid anhydrous hydrogen fluoride, HF, a rather strong acid. Not every product of biological interest can match ribonuclease in terms of resilience to acid, so I began to wonder whether a different protection scheme might be developed that would allow access to milder cleavage conditions. Taking a cue from what ribonuclease and other proteins had taught us about biochemical equilibria between sulfidyl groups and disulfide bonds, it occurred to me that harnessing any of a range of exquisitely facile methods to achieve the reduction of disulfide could be the basis of a new protecting group commensurate with this overall goal. Specifically, it's probably hard to see, look at this 5-membered ring, which starts with a nitrogen, then a carbonyl, 2 sulfurs, another carbonyl, and then back to the original nitrogen. This ring is a cyclic carbamoyl disulfide. There you hear the word in the title. And you'll hear me use the acronym DTS, which is short for dithiocyanol, as well as digital technical sound and some brand of Cadillac, to describe it later in this talk. The formal delivery of 2 hydrogens across that disulfide, which can come from ethiols or from other suitable reducing agents, breaks the disulfide, and this is followed by spontaneous loss of 2 molecules of carbonyl sulfide, COS, which is a sulfur analog of CO2. So instead of a carbamate losing 1 carbon dioxide, we have a thiocarbamate losing 2 molecules of COS. Then the nitrogen picks up 2 hydrogens from the reducing agent to become an amine, which is what we need. Now the key point here is a different chemical mechanism for temporary deprotection has now been proposed. And so the overall protection scheme can be frame shifted so that tert-butyl type protecting groups previously used temporary can be now used permanent. We'll add an anchor to the support, the parallel carboxybenzyl ester developed by Su-Sun Wang. and so the final cleavage can be done with a milder, relatively, TFA. We adopted the mathematical term of orthogonality to describe this general chemical concept of independently removable protecting groups. Although certainly this idea was in the air through work of others, it turns out that the 1977 communication to the editor of the Journal of American Chemical Society, which is from now on called JACS, in which Bruce and I announced the DTS protecting group, was also the first time that the word orthogonal appeared in print in the chemistry context. I have vivid memories of the various steps working with Bruce back and forth to make that paper crisp and focused. And I will also always treasure the classy and unique gift of a DTS lapel pin that Laurie Merrifield made in her high school arts and crafts class that year of my graduation. The major experimental accomplishment of my postdoctoral studies with Bruce was to elucidate the detailed kinetics and mechanism for DTS deprotection by thiols. And mind you, other reducing agents can be used, but you can see here that the thiol can come and break the disulfide, and we'll get a carbamyl disulfide intermediate. So DTS is a cyclic carbamyl disulfide. It's a linear carbamyl disulfide. It's a two-step mechanism. And the two steps have different physical-organic parameters. The DTS ring here is drawn in a geometrically realistic form. It's flat, it's heterocyclic, has considerable aromatic character, and that accounts for its high degree of stability in the presence of acid. That's another aspect of orthogonality. Conversely, the fact that it's flat means that the disulfide dihedral angle is 0 degrees, which is the most unfavorable it could be. Disulfides prefer to be 90 degrees to minimize p orbital repulsion. Therefore, there's a tremendous driving force for ring opening by reagents that can attack either the sulfur or the carbonyl. So the full paper describing this work with Bruce was finally accepted by JACS after 3 revisions. And this was in an era when to reorder content in a paper by cutting and pasting was done with scissors and Scotch tape rather than with word processing software. To make the little-known adage about fourth time is a charm come true, Bruce wrote a particularly forceful cover letter stating that while the latest revision was certainly different, we'd gone beyond the point where it was any better than the preceding version. Now, with 9 rewarding years at Rockefeller under my belt, Bruce encouraged me to get out on my own. We also reached an understanding that I could work independently to further develop the chemistry of carbamyl disulfides. Thinking back on that anxious transition period in my life, I realize now how well it reflects on Bruce's character and integrity. Telescoped into this one slide are some of the myriad applications of this chemistry that, for the most part, were worked out in Minnesota. The original vision of DTS amino acid building blocks for mild orthogonal solid phase peptide synthesis met with both successes and disappointments, but additional opportunities arose with peptide nucleic acids, or PNA, and with glycopeptides. Now, since DTS covers both free valencies of nitrogen, it clearly could not be used on the alpha imino group of proline, but fortunately we were able to develop a suitable open-chain carbamyl disulfide variant. Next, we figured out how to invert our mechanistic understanding of DTS dialysis by developing a stable carbamyl disulfide derivative to protect cysteine residues in peptides, and to also activate these residues for directed disulfide formation, both intra and intermolecular. And related work used DTS derivatives directly to oxidize appropriate peptide precursors with free sulfhydryls. We discovered that trivalent phosphorus could readily pluck out a sulfur from DTS, leaving behind an isocyanate after loss of carbonyl sulfide. So we can get mass isocyanate. Now, applying this to a DTS amino acid, this chemistry becomes an especially mild way to access the corresponding N-carboxy anhydrides, and when working with DTS amino acids, they are analogously converted to hydantoins. Again, an inverse look at this reaction, focused on phosphorus, provided a superior way to convert trivalent phosphoramidite precursors into the pentavalent phosphorothioate functionalities that form the backbone of antisense DNA and RNA. And finally, I should mention that alkylation of the DTS derivative of ammonia provides a very mild version of the classical Gabriel synthesis of amines that involves alkylation of phthalimides followed by hydrogenalytic deprotection. Now, Bruce followed a work in all of these areas and others with considerable interest and was always upbeat and supportive about it. I want to spend the next few minutes discussing methods for the synthetic construction of the DTS ring, including fascinating mechanistic aspects, as this tack will lead us to yet another revealing anecdote about the man whose memory we honor today. reactions of thionourethane derivatives, and here I show the ethoxythiocarbamoyl or etc. derivative, with this interesting bifunctional reagent, chlorocarbonyl sulfonyl chloride, results quickly and with reasonably high yields in the formation of DTS. And the alkyl chloride and HCl are formed as coproduct. There's also a dead-end pathway, and so whatever of the starting material is not converted to DTS makes its way to carbamoyl chloride, and we lose, again, the alkyl chloride, COS, and elemental sulfur. Now, in the presence of base, the results are quite similar, except, of course, the base will neutralize the hydrogen chloride, and the dead-end byproduct is now an isocyanate. Now, when R is hydrogen, we don't come here, but we go to this interesting compound shown in the box, which we affectionately called Edith, after my kindergarten girlfriend. Also, when R is carboethoxy, which was an attempt to make the DTS analog of the Nefkens reagent, now that's a compound that reacts with amino acids to directly produce phthalate derivatives. Those are not failures, but it did give a chance to isolate and characterize some intermediates along the way. Now, our mechanistic bottom line, supported by numerous lines of investigation, is this. An initial adduct is formed which rapidly collapses with loss of HCl to give this intermediate, which then loses ethyl chloride to give DTS. If ethyl chloride loss occurs first, then DTS is not produced finally, but let's hold that thought because I'll get back to it shortly. I want us first, though, to ponder the thought that we're starting here with a derivative of the mean, so we already have one step to get here. Wouldn't it be nice if we could come up with a single-step reagent for forming DTS derivatives? So this takes us back to still when I was at Rockefeller, where I found in the literature 2 papers describing ways of making bischlorocarbonyl disulfide, the reagent shown in the box. Now, one of these methods was hopelessly complicated and involved specialized equipment, but this method seemed reasonable enough to try, but for whatever reason, I couldn't get it to work. So I therefore developed the procedure shown here, and it was mentioned in our original Jack's communication with Bruce, but I revisited later in Minnesota and worked out the various steps, scale them up, optimize them, figure out mechanistic issues, and that was my first full paper out of Minnesota. So the question is, was it worth the effort? And so we got this hard-won reagent, and the idea is react with amine, get this intermediate, but we never, ever isolated, despite numerous efforts in playing with conditions, the desired DTS derivative. Most frustrating. And moreover, we developed some alternative methods to get to these intermediates, which are called chlorocarbonyl carbamoyl disulfide. But again, we never got DTS at the end. That, even though that certainly seems reasonable intuitively. So these are stable derivatives, we don't get DTS. So we're kind of at a dead end, and I'd pretty much given up on the problem. But a few years ago, my son Michael, who was then in high school, informed me that he wanted to find out what it was like to work in a chemistry lab. I realized that Michael's project needed to be one that I had personal hands-on experience with, so we could work together, and I wouldn't have to foist him on any of my other coworkers. During a lab cleanup that preceded any real work, we found a bottle of a reagent called heptamethyl disilazane, and I remember that Bob Hammer, who had been a graduate student with me in the late 1980s, had ordered this. By now he's a full professor at the Louisiana State University. But at the early time, he'd speculated that maybe the problem with why we weren't getting DTS was we were producing HCl. And if we could replace that by a neutral trimethylsilyl group, maybe something nice would happen. So I suggested Michael should revisit Bob's idea. So we located a test tube of bischlorocarbonyl disulfide, which was still as fresh as the day it had been made before Michael had been born. It was still good. And then we reacted with Bob's compound. Here's HCl, and that leaving group is going to be replaced by a trimethylsilyl group. It worked like a charm the first time. So beginner's luck seems to run in the family. Now you can study the chemistry in the slide and note the reference on the bottom while I deliver my promised story. Realizing that the intellectual roots of the work went back to my graduate work at Rockefeller, I asked Bruce if he would consider being a co-author of a communication that we were contemplating to submit to Jack's. To our delight, Bruce accepted enthusiastically and made some incisive suggestions to improve the manuscript. Bruce was up to speed on the work from our regular conversations and had met Michael several times, in Minneapolis on the occasion of the 16th American Peptide Symposium, in his Rockefeller office, and at the Merrifield homestead in New Jersey. There was only one hitch. Before the paper could even be sent out for scientific review, a clerical assistant in the editorial office summarily rejected it on the grounds that, by journal policy, author first names had to be spelled out rather than initialized. I called Bruce for advice, and he pondered this development. As we've heard, the journal had just recently completed a milestone anniversary and compiled a list of its most cited articles. Bruce's landmark sole-authored 1963 papers introducing solid-phase peptide synthesis to the world was number 5 on the list, something Bruce was quite justifiably proud of. Bruce said, and I can't really do a good imitation of his voice, "Just tell them if RB was good enough for their 5th most cited paper, it should be good enough for this one." And so you can see the symmetry here. I published my first paper with Bruce when I was 17, and Michael, my son, published his first paper with Bruce when he was 17. This multi-generational paper, which also includes Bob Hammer, is a highlight of my life. I want to share some closing thoughts. Bruce Merrifield was like a second father to me. I knew him for just a shade under 35 years, and I'm older now than he was when we first met. He was a down-to-earth man with a razor-sharp mind, a keen sense of history, and a respect for others. He was devoted to his family, and he never asked for pity. He and I talked about many things beyond chemistry, a few which will have to remain private, and the majority of which, were I to recount, would keep me at this podium until past everyone's bedtime. And you've heard about them from the other speakers. He taught me many things, including his emphasis on the need to stay at the bench and his simple do's and don'ts for written and oral scientific exposition, which I will try to follow. Thank you, Bruce, for the gift of your life and for the gift of bringing us together one more time in your absence. Your contributions were legion, and your memory is immortal. You inspire us to carry on. Thank you.
The next speaker is Richard DeMarchi, and he came to Rockefeller in October